So in this section, I want to talk about limits at infinity. That's a little bit different than when we're talking about infinite limits, limits that could equal infinity or limits that could equal minus infinity. What we're talking about here is given a function f, let's take a look at the limit as x goes to infinity of f of x. What that means is as x gets more and more positive, bigger and bigger and positive, what happens to the value of f of x? So for the most part, we'll consider f to be a polynomial or a rational function. Focusing on rational functions. But we'll talk a little bit about polynomials too. So again, as x gets very, very big, what happens to the y value of the curve y equals f of x? We'll also talk about limits as x goes to minus infinity, as x gets big and negative. So here, if we take a long walk off to the right, what's happening to the y values? And here, if we take a long walk off to the left, what's happening to the y values? Let's do some that are fairly obvious. Let's take a look at the limit as x goes to infinity of the function x squared. So as x gets to be a bigger and bigger positive number, what happens to the value of x squared? So if you take a very big positive number and square it, you get a huge positive number. And so I think you can see that as x gets very big and positive, so does x squared. So this limit equals infinity or plus infinity. So I just wrote infinity here. You can put a plus in front of it if you want to emphasize the fact that it's plus infinity. And if we take a look at the curve, y equals x squared, you know what that looks like. It's just a parabola. Then as x gets very big and positive, as we move to the right along this curve, you can see that the y values are also getting very big and positive. And if I ask you about the limit as x goes to negative infinity of x squared, so as x gets more and more negative, as it gets bigger and bigger but negative, what happens to the y values? Well, you can see it on the curve, or you can reason it out algebraically. As x gets very big and negative and you square it, you get a really big positive number. So this is also equal to plus infinity. And again, you can see it on the picture. As you take a long walk off to the left and keep checking these y values, they're shooting up to plus infinity. Let's take a look at an example that's not so obvious. This time I'm going to take a look at a rational function. Let's take a look at the limit. Well, let's take a look at another relatively simple example before we get really complicated. Limit as x goes to plus infinity of 1 over x. So as x gets very big and positive, what happens to 1 over x? Well, you can try a few numbers in your head. If x is 10, then 1 over x is 1/10. If x is 100, 1 over x is 1/100th. If x is 1,000, 1 over x is 1/1000. So as x gets bigger and bigger and positive, I think you can see that 1 over x is getting closer and closer to 0. And what happens as x goes to negative infinity of 1 over x? So as x gets very big and negative, again, you can try numbers in your head. So 1 over negative 10 is negative 1/10. 1 over negative 100 is negative 1/100th. So again, as these numbers get very big and negative, 1 over x is getting closer and closer to 0. And again, if you happen to have the curve y equals 1 over x in front of you, you can see it on the picture. We know y equals 1 over x. Looks like a hyperbola centered at the origin, opening in the first and the third quadrants. And as we take a long walk off to the right and keep checking these y values, they're going to get closer and closer to 0. And as we take a long walk off to the left and check the y values, they are also getting closer and closer to 0. And I think you can see that if I have the limit as x goes to infinity of, say, a number over any power of x, as long as this power is greater than 0, then as x gets very big, x to the n is going to get very big. This whole expression is going to get very small. Here, a is just a constant. And so this gets closer and closer to 0. And it's the same for the limit as x goes to negative infinity of a over x to the n. This is also going to get closer and closer to 0. All right. Let's take a look at something that's a little less obvious, and we'll need to do some more algebraic work. Let's take a look at the limit as x goes to, say, plus infinity of, let's make it 2x squared minus 3x plus 1 over 4x squared plus 5x plus 6. Okay, so here, as x gets very big and positive, I think you can see the top is a parabola, right side up parabola, and so is the bottom. So as x gets very big and positive, the top gets very big and positive. And as x gets very big and positive, the bottom gets very big and positive. So that doesn't really tell us anything. As the top gets big, it's trying to force the whole thing to be bigger and bigger. And as the bottom gets big, it's trying to force the whole thing to be smaller and smaller. The bigger you make the denominator, the smaller you make a fraction. But they're both getting big. So what happens in the long run? I'm going to show you an algebraic trick right now. The most important thing to remember about this algebraic trick is that you only use it when x is going to infinity or x is going to minus infinity. Don't use it if x is going to a number. So we can only apply it in this situation. Very important. What we're going to do is we're going to take this expression and we're going to multiply it by the number 1 in the form of an expression divided by itself. The expression that we're going to take the largest power of x. You can see it's the same on the top and the bottom. And I'm going to multiply by 1 over that largest power of x. And since I have to multiply by the number 1, I have to do the same thing on the top and on the bottom. This is easy if the top and the bottom have the same degree, which they do in this case. They're both degree 2. Let's see what happens. The limit as x goes to plus infinity, 2x squared times 1 over x squared. The x squareds cancel out, and you're just left with the number 2. Minus 3x times 1 over x squared. One of the x's on the top cancels out with one of the x's on the bottom. So instead of having an x squared on the bottom, we just have an x. And so we have minus 3 over x. Did everybody get that? If we take the minus 3x and you multiply by 1 over x squared, you end up with minus 3x over x squared. So you can cancel this x with one of those on the bottom, and you're left with minus 3 over x. If we just multiply the 1 by the 1 over x squared, we end up with 1 over x squared, of course. And let's do the same thing on the bottom. 4x times 1 over x squared. 4x squared times 1 over x squared. The x squareds cancel out. We're just left with 4. 5x times 1 over x squared. Same trick. We're going to end up with plus 5 over x. 6 times 1 over x squared. That's 6 over x squared, of course. So we end up with this compound fraction. Fraction with fractions on top and fractions on the bottom. And certainly, at first glance, that looks worse. I would say this looks worse than that. But in light of what we were talking about over here, let's take a look at what happens to these fractions as x gets very big and positive. As x gets very big and positive, what happens to 3 over x? If you take 3 and divide by a larger and larger and larger number, that goes to 0. As x gets very big and positive, you take 1 over x squared, a larger and larger and larger number on the bottom, that's going to 0. Likewise, this is going to 0. And this is going to 0. All 4 of these are going to 0. You're left with 2 over 4, or 1/2. Please remember, only use this trick if x is going to infinity or x is going to minus infinity. Don't use it if x is going to a specific number. You already know a lot of tools when x is going to a specific number. Factor and cancel, rationalize the numerator. You have a lot of tools under your belt. This one won't apply. Only if x is going to infinity or x is going to minus infinity. Let's take a look at another example. How about we take a look at the limit as x goes to, let's make it minus infinity, it doesn't really matter. X goes to minus infinity of the fraction. Let's make it x squared. Now let's make it 3x squared plus 2x plus 1 over x cubed minus 4x squared plus 2x minus 11. Now we don't have the same degree in the numerator and the denominator. I'm going to take 1 over the largest power of x in the denominator here. So I have to multiply by the same thing on the top and on the bottom. Otherwise, I'm changing something. You can only multiply by 1 without changing something. So it has to be the same on the top and the bottom. I'm going to multiply by 1 over the largest power of x in the denominator. The largest power of x in the denominator is x cubed. I'm going to multiply by that. And let's see what happens. Let's multiply this all out. Again, it's going to look worse for a second. Limit as x goes to minus infinity. 3x squared times 1 over x cubed. That's 3x squared over x cubed. 2 of these, so the x squareds cancel with 2 of these. We're just left with x in the bottom. So we just have 3 over x. Likewise, 2x times 1 over x cubed. This x cancels out with 1 of these, leaving with an x squared in the bottom. So 2 over x squared. And 1 times 1 over x cubed is certainly 1 over x cubed. I don't know if that's clear. That's a 2. X squared. And on the bottom, we end up with x cubed times 1 over x cubed. That's just plain old 1. Minus 2 of these cancel with 2 of these, so minus 4 over x plus 2 over x squared minus 11 over x cubed. After we do all the multiplication, and if you need to catch up, please feel free to pause the video here. And that certainly looks worse than it did in the previous line. At least it does for a second, because as x gets very big and negative, 3 divided by x, that's getting closer and closer to 0. So's this. So's that. So's this. So's this. And so's that. And so we have 0 plus 0 plus 0, that's 0, over 1. On a good day, that equals 0.